Hello everybody, how are you today? Today we're going to look at Fourier Transform. Okay, Fourier Transform is also denoted by ft and is defined in the infinite interval. Okay, so we want to look at the definition. The definition of Fourier Transform is given by f hat omega equals to minus infinity to infinity fx e negative I omega x dx. Okay, in another word, Fourier big capital F Fourier transform of fx is given by f hat omega. Okay, this is the definition for Fourier transform. Now, I want to show that this Fourier transform of f a plus ax plus b, Fourier transform of f ax plus b equals to 1 over a e I b omega over a f at omega over a. Okay, we want to show this. Okay, to show this, we need to use the definition. Okay, by the definition, we have f hat omega equals to minus infinity to infinity fx e negative I omega x dx. Now, this is our fx. Okay, this whole thing is my f hat omega. Okay, so putting fx into here will give me minus infinity to infinity f of ax plus b e negative I omega x dx. Okay, now the next step will be to solve this. Okay, how to solve this? Before we do this, for simplicity, we will say let y equals to ax plus b. So we have here ax equals to y minus b, x equals to y minus b over a, and here you differentiate respect to x. So dy dx equals to a dy over a equals to the x. Okay, once you've done that, you're going to put it into this integral. So we have f hat omega equals to minus infinity to infinity f of y, this become my y, e negative I omega, and my x will be y minus b over a, and the x will be dy over a. Okay, now what's the constant here? 1 over a is a constant, fy, and I can split this integral into e negative I omega y over a, minus minus will be positive, e I omega b over a. Okay, d omega, dy. Okay, are you with me? So what happened here? So you just split the integral e negative I omega y over a for this one, and negative will be positive, e I omega b over a. So in other words, I have this one, a alpha beta plus b plus c. So how do you write this? You have e alpha b e alpha c. Okay, this is what happened here. Okay, so what happened here now? This is nothing to do with y, so I can bring it as a constant. So I have 1 over a ei omega b over a. Okay, now we have from minus infinity to infinity f of y, ei omega negative I omega y over a dy. If you look at this integral, this is similar to the definition, because the definition of Fourier transform from minus infinity to infinity f of x. Okay, let's write the definition. Minus infinity infinity f of x e negative I omega x dx. This is the definition of Fourier transform. Okay, so if you look at here now, the difference is this one. Now we have omega over a. If this is known as half hat omega, so you will have 1 over a e I omega b over a f at omega over a. So I have shown you the Fourier of f ax plus b equals to 1 over a e I omega b over a, and so on. Okay, so this is by definition. Now let's look at one example on how to use this formula. Okay, the example will be, find the Fourier transform of fx equals to 5e negative x plus 2. Okay, so this is the example. Now we know f of Fourier of a plus ax, Fourier of ax plus b is equals to 1 over a e I b omega over a f at omega over a. So we need to use this. Okay, so first of all, how do you do this? So we have Fourier of 5e negative x plus 2. Now by the linearity property, I can take 5 out, leave me with Fourier of e negative x plus 2. Okay, now my function, my f function here has x plus 2. Okay, that's another thing. Okay, we have x plus 2. So what happened here? Now we're gonna find it f of Fourier of f of x plus 2. Okay, so what do you have? My a is 1, my b is 2, so that will give me 1 over 1 e, I'm using this formula, I, b is 2, omega over 1 f hat omega. So I have e I 2 omega f hat omega. Okay, so now this will leave me to, so what I have here, so what is my f hat omega? My f hat omega now will be this part here will be the Fourier of e minus x, modulus of minus x. Okay, so we have evaluated this part here. Now all we left with this, and this is by the definition, by the Fourier table. Okay, table, Fourier of e negative modulus x is given by I think the definition is given by this. If I'm not mistaken, it should be minus a modulus x is given by 2a over omega squared plus a squared. Okay, so in my case, my a is 1. So Fourier transform of e negative modulus x is given by 2 over omega squared plus 1, because a equals to 1. Therefore, now my final solution, what we do here, we want to find, the question asks you to find Fourier of 5e negative x plus 2. Now putting all the pieces back, we have earlier on 5 e2i omega Fourier of e negative x, which is 5 e2i omega, this one, 2 over omega squared plus 1. Okay, therefore your answer will be 5 times 2 is 10 e2i omega over omega squared plus 1. Okay, so this is the Fourier transform using the property of this one. Okay, so the Fourier transform, if you are given a Fourier transform of a function different than the given in the table, so we have to use this definition. Okay, and all you need to do is you have to transform this first, make it as the original as the table. Okay, and to transform this, you need to use the Fourier transform of f ax plus b equals to 1 over a, and so on. And then whatever left now this can be found from the table. Okay, this is given from the table. Okay, and then you put back into the equation. Okay, so that's all for today. We'll see you in the next video.